Hi everyone, Mr. Boltri here, bringing you a video 2.3 where we're going to talk about weight and drag. So weight is a synonym for force gravity. And as I do this video, I'm going to use those two terms interchangeably. So what we're going to cover today is an experiment where we're going to investigate the relationship between mass and weight. So I'm going to take you through the experimental setup and then the experimental results. And then to close the video, we're going to talk about drag force and terminal velocity. So this experiment is pretty simple. I'm just trying to figure out what is the relationship between the mass of this mass hook right here and the weight or the force gravity acting on the mass hook. So to do that, I have a bunch of masses, an electronic balance to check the masses. I have the mass hook and a force probe connected to Logger Pro so I can check all the forces. So it's a pretty simple setup, but before we do the actual experiment, we need to make sure that we understand everything that's going on. So here I've circled the mass hook and the force probe. And I would like for you to pause the video really quickly and do a force diagram for each of these two things. Okay, so hopefully your force diagram looks something a little bit like this. So on the mass hook, I have force gravity and the force applied, the upward force that's keeping it from falling down. And then on the probe hook, I have the downward force of this mass hook pulling down, plus the force gravity. Don't forget that one. This is an easy one to forget. And then the applied force that the force sensor is applying to the probe hook. So also when you do your force diagrams, don't forget equality marks. So over here, the whole system is stationary. So therefore, I know that it is maintaining a constant velocity of 0 meters per second. We know according to Newton's first law that constant velocity gives us balanced forces. So everywhere in this, the forces need to be balanced. So over here, all the downward forces need to equal all the upward forces, so we can add equality marks there. And then you'll notice over here, all the downward forces equal all the upward forces, which is why this force applied is a little bit longer. But we can't add any equality marks over here because none of these forces are equal to each other. They just happen to be balanced out. Okay, so you might be tempted to look over here and say, aha, I noticed that there are two forces that are equal in magnitude and opposite in direction. So that might be a Newton's third law interaction force pair. But I wanted to make it very clear that that is not true. These two forces are balanced because of Newton's first law. Because the object has a constant velocity, the forces are balanced. And we can see that it's not a Newton's third law interaction force pair if we look at the what is doing the force and what is receiving the force. So remember, in a Newton's third law interaction force pair, the bi-ons have to be flipped. Bi A on B pairs with bi B on A. So for example, bi probe hook on mass hook pairs with bi mass hook on probe hook, which is actually a force that we can see in this force diagram right here. Bi mass hook on probe hook is equal in magnitude and opposite in direction of the force by the probe hook on the mass hook, because this force and this force are an interaction force pair, Newton's third law. This force and this force are balanced forces according to Newton's first law. Balanced forces, constant velocity over here, interaction force pairs between this one and this one. So that's kind of a common misconception. Just because two forces are equal in magnitude and opposite in direction does not mean that they are an interaction force pair. It's also the bi and the ons have to be flipped because it's the probe hook and the mass hook interacting with each other. So before we move on, the one tricky thing about this lab is that we are trying to measure the force gravity. And we're trying to measure the force gravity by using the force sensor. But the reading that the force sensor actually measures is this one, the force applied by the force sensor. It knows how much force it is applying. And you'll notice that this force applied by the force sensor is not equal to the force gravity. It would be if we could ignore this, the force gravity, the gravity of this tiny little force hook. But because this force hook does have non-negligible gravity, and I forgot to calibrate the scale to ignore the non-negligible gravity of the hook, this little hook, our results are going to be a little bit off. So I wanted to celebrate mistakes, and so you can remember in a minute when our results are a little bit off, that it's because of the force the mass, we're going to have a little bit of extra mass right here. So without further ado, let's look at the results of the experiment. So I have the mass here in kilograms, which is the base unit, and then I have the force gravity in newtons, also the base unit. So thankfully, this graph looks to be linear, so we don't have to do any linearization like we had to do in the Newton's second law lab. We can just draw a line of best fit and write the equation. So a common question might be, okay, so if this is the experimental value, 10.11 times the mass, and what we were expecting was 9.81 times the mass, what could have caused that? And so obviously we are overestimating the amount of gravity. Because when we take this and multiply it by the mass, we get too much force gravity based on what we were expecting. So it appears to be that there is some extra mass somewhere in there that is causing us to overestimate the force gravity. And then remember from earlier, one possible explanation for that might be the mass of the mass hook wasn't zeroed out when we started the experiment. But remember, we don't have to use 9.81 in this class. You can just use force gravity equals 10 times the mass. And this is a formula that you're going to want to memorize because it's not given to you on the formula sheet. But like with most formulas, there's a big caveat on when we're allowed to use it. So we are only allowed to use this formula if the problem happens to be on the planet Earth. Because a more general formula would be that the force gravity equals the acceleration due to gravity times the mass. And so the acceleration due to gravity on Earth is 10 meters per second squared, but on the moon it might be a different value, and on an alien planet might be another different value. So, and you'll notice that this formula actually equals or is a specific instance of Newton's second law, the FAM law, force equals acceleration times mass. It just happens to be that the force due to gravity equals the acceleration due to gravity times the mass. So write down both of these formulas, and these are both going to be ones that you're going to want to memorize because they are not given on the formula sheet. But it's useful because anytime you are given the mass of the object, assuming it's on planet Earth, you can go back and forth between mass and force gravity just by multiplying by or dividing by 10. Okay, so now to wrap up the video, let's talk about, well, what is drag? So I guess that's an acceptable answer to the question, but I should have said, what is drag in a physics concept? And drag in physics is a drag force, I should have said, and drag force is basically air resistance. But we don't call it air resistance because it could also be drag force if you're like swimming in water. That's also drag force. It's just the force of a fluid, any fluid, which is air or liquid, pushing back against you. So what is the formula for drag force? You do not have to memorize this, and it's not given on the formula sheet. You just have to understand what are the factors that cause drag to be bigger. So drag force equals 1/2 times the fluid density times the relative velocity times the drag coefficient times the surface area. Okay, so that's a lot. What does that mean? Fluid density. Basically, if you've ever tried to like throw a ball underwater, you'll notice that it doesn't go as far as if you throw it in the air because the water has a higher fluid density, so therefore it experiences more drag force. What is relative velocity? Well, if you're running really fast, you might feel more drag force, or like planes feel a lot of drag force. So that's velocity. But relative velocity is, for example, if you're running really fast on a windy day, you're going to experience even more drag force. So it's not only your speed, but it's also the speed of the fluid that you're in. Drag coefficient is just a number that incorporates things such as texture, like surface texture, and shape. Because surface area, this is why like parachutes work. If you open up the parachute, there's a lot more surface area for the air particles to hit, and it's going to cause you to experience more force drag. In all of these circumstances, the big question is, what is going to cause me to hit more air particles, air molecules? Because the more air molecules you hit, the more force drag you're going to experience. So fluid density, there's just more there to hit. Relative velocity, if you're moving faster, you're going to hit more. Drag coefficient it just causes you to hit more, and surface area, more area, you hit more air particles, air molecules. You'll notice that nowhere in this formula is mass because your mass does not change the number of air particles you hit. You could have a really dense mass, or it depends on the area, but not the mass, because it all has to do with the number of air particles that you hit. So what does this mean in like an actual context? So if we're thinking about a skydiver, as soon as they jump out of the plane, their velocity is zero. If the velocity is zero, assuming there's no wind, then this relative velocity is going to be zero, and there's going to be no force drag. So the only force acting on them is going to be the force gravity acting downward, which is going to cause them to accelerate. As they accelerate, they're going to move faster and faster and faster. As they're moving faster, the relative velocity is going to increase, so then the force drag is going to increase. As the force drag increases, the net force acting on them decreases. You'll notice that this positive number added to the negative number makes the net force, the sum of these two forces, smaller. According to Newton's second law, as the net force gets smaller, the acceleration also gets smaller. But the person is still speeding up, falling down. They're just speeding up less. So they're speeding up less, but still speeding up. So now their velocity is going to be even bigger. So that's going to cause the drag force to be bigger, which is going to cause the net force to be smaller and the acceleration to be smaller. And that's going to keep happening over and over and over until the person is moving so fast that the drag force actually equals the force of gravity, and the person is going to stop speeding up. Their acceleration is going to be zero, and they're just going to keep moving at that same velocity until something changes. So one thing that could change, and one thing that often changes, is the person opens the parachute, which causes the drag force to be even bigger. And then their acceleration is positive, and then they slow down. But this state right here, when the drag force equals the gravitational force, is called terminal velocity. And that's when you've been moving faster and faster and faster to the point where you can't move any faster. Your acceleration becomes zero because of how large the drag force has become. So that is sort of a just very quick overview of two common forces that we're going to see in this class, weight and drag. We're going to do some practice problems on both weight and drag in our next class. But if you have any questions, please do let me know between now and then, or just at the beginning of class. But this is Mr. Boltri wrapping up video 2.3 on weight and drag, and go Bears.